So I have the pleasure of introducing this afternoon's keynote speakers. So our first session will be presented by Craig Muntz and Eric Enderbrock. Craig Muntz is VP of one too many S's there, SSD development at Micron, where he's responsible for the development and engineering on all SSD products. He brings his extensive experience on storage R&D and his leadership to help transform Micron's SSD portfolio, particularly at the cloud and enterprise segments. Previously, Curry was VP of SSD development and VP of Research and Advanced Technology at HGST, where he led the development of all SSD enterprise products. Curry has also headed research for HGST and IBM Storage Systems Division, where he was responsible for invention and development of future technologies and early stage prototyping and development of new products. Curry holds a PhD in mechanical engineering from Stanford and a BS in applied mechanics from the University of California at San Diego. He is frequently quoted in trade and technical press and has appeared at many conferences. Joining Curry is Eric Enderbrock. Eric is VP of Storage Solutions Marketing at Micron, where he focuses on positioning Micron as a world-class enterprise storage brand. He has led the introduction of Micron's first NVMe drives, as well as other state-of-the-art products, including its recently introduced solid-scale platform architecture. Before joining Micron, Eric was Director of Product Management and Business Development and an M&A integration executive at Dell, where he was responsible for integrating the Equalogic acquisition into Dell's corporate structure. Eric holds an MBA from Australia's Monash University and a BA in accounting from University of Nevada at Las Vegas. He holds 5 patents in iSCSI networking and is a popular Micron blogger, writing about topics such as flash in the data center, SSDs, data analytics, and big data. Please welcome Eric Enderbrock.
We have over 325,000 customers participating in the capital market, and our job is to help them understand kind of the flow of information. There are over 100 billion ticks of market data every day that flow through our system, and over 1.5 million news stories a day. And so how do we help them understand kind of those tools?
What is happening is the variety of data types that we have to deal with. It's not just a transactional workload, analytical workload, streaming, and especially some of the new machine learning and other applications that are emerging has unique and new and different characteristics. Because you've got all the other attributes, why do we want to have disks at all? I don't want to have hard disks get to flash.
I think one of the key things that Flash has done is being able to kind of provide that consistency in the data retrieval, and so that way we know, when we're delivering information to a customer, that they'll be able to get it within its expected SLA. One of the great trends that we're seeing in the data center around flash is the introduction of NVMe, and we really think that is going to be the next step in kind of improving the latency characteristics of flash storage in the data centers.
Other attributes related to flash is we look at not only from a performance standpoint, we look at the availability metrics we can do, because we not only want to do backups faster, we want to recover faster, because when you have an in-memory database with a huge footprint, recovery is very important. How do you do very fast recovery, which means you need to read a lot of the data that is backed up very fast.
We're able to take kind of this low latency, kind of high performance storage and be able to leverage techniques like machine learning and be able to kind of look at all the data as it passes through and be able to apply models to it to kind of say whether the market is relevant to our customers and be able to present that to them, and hopefully they can take action on it. We handle a whole bunch of news information, and we have over 500 news stories a second that come in, and with using flash storage, we're now able to deliver them to our customers in under 100 milliseconds.
Well, good afternoon, and welcome to Flash Memory Summit. I usually start off these and kind of tell a little anecdote, and I thought today maybe I'd do something a little bit different. given how difficult events like this are to put on in the best of times and chaotic, today maybe even a little bit more chaotic, and if you're just new, they've had some events around here that have made today's show particularly exciting. And we're all in the storage industry, and storage industry is about resiliency, recovering, and doing that really quickly without impacting the business. And I just wanted everybody to maybe just do a really quick applause for the Flash Memory Summit crews, the facilities people, because we had a little fire this morning, if you didn't know about it, and it's put everybody off their shoes, and they've done an amazing job. You can't even tell that it probably happened. And so just everybody clap for these guys. They worked really hard. All right, my name's Eric Enderbrock, and I think you got all the details from the announcement. Wanted to talk really quickly about some trends and what we're seeing, and we call it kind of insights from systems to silicon, or silicon to systems in our case, all the way from the foundational elements of what we're doing and taking those insights and learnings and changing how the world operates. And it really comes down to a couple real key things. You heard Bloomberg, SAP, our customers that we work with every day, talking about some of the problems they're trying to solve. And in the next kind of 20, 25 minutes, we're gonna walk through some of those and what we're doing about it. But fundamentally, it all comes down to what we call these 3 V's. These are the V's of big data and of the modern workload, and it's volume. So everybody understands this one. We're creating data at an amazing pace. Something like 163 zettabytes by, I think it's 2025 is the plan. That's something like 25 zeros. So data is just inflowing at rates and being created quicker than we've ever seen. Mostly machine to machine, but that data is still coming in. And that brings you to the second one. It's not just that it's coming in, it's being created, it's how fast it's coming in. We heard the gentleman from Bloomberg talking about something like 100 billion impressions a day that he's got to feed his user base. Or that's 5.9 trillion tweets a day, or 160,000 images that Facebook uploads every minute. And so this velocity of data, and then trying to do something with it with automation, advanced AI, and machine learning is just crushing the systems of today. And then the last one, if not enough that it was a lot of it, and that it was coming very fast, the next part is there's too many kinds of it, structured, unstructured. It's everything from databases, rows and tables, and bits and bytes, but now images, audio files, every part of this that you have to consume and somehow do analytics and produce results on. And so that's the challenge that we're facing, this modernization of the infrastructure to turn that. And so as we talk today, I wanted to walk you through a very high-level system architecture. This is a very simplified version of what that might look like. You can kind of see across the top, you got everything from memory, fast storage, primary storage, software, solutions, CPU, networking, lots of different things that go into an architecture. And it's the work Micron's doing with our customers, the work that's happening in this room that's actually helping customers solve these challenges and problems. And so I don't think there's ever been a time where our industry has been more relevant to solving the challenges of the future. And so let's dive right into it. As you kind of build this out, I wanted to talk a little bit about memory. Let's start there. So obviously DRAM, something that's foundational to Micron. We've been a 30, 35-year company building DRAM solutions. But it's moving now more into the persistence. So memory is a piece of it. You need to be very fast. It's closest to the CPU. But now it's even more important as in-memory databases and the analytics of the future approach $14 billion market by 2022 that we really address and we broaden what this world looks like. And so to do that, I'm going to invite Curry Muntz out on stage with me as well. He's going to help out and make this a little bit more lively. And I will tell you one anecdote. They tell you in show business, don't work with, children, animals, and marketing people. Well, I think Curry might have at least violated 2 of those in saying yes to this. So welcome, Curry.
Thank you, Eric.
Appreciate it. So as you kind of think through this, you have the traditional memory hierarchy, and it goes across memory semantics and storage semantics. And so obviously at the very fastest end, very closest to the CPU, but giving you the most performance, you can see NVDIMMs and persistent memory. This is really important. NVDIMMs, combination of DRAM and NAND sitting on a memory bus, is an important part of an architecture. It's closest to the CPU, but it gives you the resiliency It gives you that data residency, so it's very close there, and your data is protected. Again, something that's very important to us in this market.
Great point, Eric. It's always really been about tiering. We've never been able to afford to put all our data on the fastest storage out there. If I were up here probably 10 years ago, I'd be talking about tiering. I'd be talking about how we're tiering 7200 RBM drives to 10K to 15K. What you're seeing here really is an exciting proliferation of the number of solid-state devices, though, that sit between spinning disk and DRAM and compute. It's really all about how we get information and data to the CPU, to the processing, more efficient operations, more power efficient and faster operations. And in each one of those new technologies, they all have a little bit of different quirks, different behaviors, different operations. So really trying to understand all those and how they're going to work together is really important in trying to build out the data center and use these. And what's exciting to me at Micron is from the flash, the DRAM and NVDIMM, from the 3D XPoint to the NAND flash and SSDs, Micron is actively engaged in all those technologies. So it's a very exciting opportunity for us to figure out how to optimize and bring those all together to solve these kinds of problems.
Yeah, you bet. Thanks, Curry, for that. So as you kind of move down the hierarchy, then you kind of touch to fast storage. Fast storage is interesting. That used to mean SSDs. That's no longer the case, but we'll get to that in a moment. Now we see this blurring of fast storage sitting on the NVMe bus and moving over and connecting into the memory pieces. And this is very important. And it's really about creating the lowest latency, a solution that really ties together the memory and the storage in a way that can feed the largest and most demanding workloads. So a very interesting part. Let's kind of dive into that. And it gives me the great pleasure to announce our 9200 NVMe SSD. This is actually a follow-on to a breakthrough product for Micron. And this is the first product that's using our 3D NAND flash in a high-performance NVMe SSD. So very exciting for us. And it does a couple things for us. Allows us to really reach higher capacities. Capacity is becoming a really key attribute within an environment. And so once you move past traditional hard drives in storage and beyond what we've traditionally thought of as a cache layer within a system architecture, capacity starts playing a more important role in creating the dollars per gigabyte that return value across the environment. This is a very interesting one. So obviously very high performance. It's something like 4x the capacity. It's at least 30 to 40% faster across all the normal specs. So you think about read IOPS, write IOPS, and throughput. We've seen improvements on every one of those across the board for our 9200. And while you might look at it and say, well, 11 terabytes is kind of maybe not that big compared to what what we've seen. As a high-performance SSD, we're really targeting our mainstream user base. We're focused on relevant specs, relevant speeds, and delivering the best experience with what our customers are demanding and what they're looking for in a drive that's close to the CPU with extremely robust performance. And of course, spec sheets is all just spec sheets. What it really matters is once you stick it into a system and what does it do. And we ran this drive in an OLTP workload and against a popular database, and we found that it was 45% faster than its nearest competitor, almost 2 times the capacity of what they're selling. So the results are there in a mixed write and read workload. But even IOPS and those kind of performance, those are just one element of it. It's really about the latency. And I'm going to let Curry talk a little bit about those impressive results.
Well, flash brings us a lot of speed, but speed without control is not useful. It doesn't matter how big the engine in your car is when you got to go around that hairpin turn. It has to do with how you can control. You heard in the opening video about customers talking about latencies, about consistencies, about service levels agreements. So we've got to focus not just on speed, but how are we addressing control? How am I getting the information back? Not on average, how am I getting it back? Worst case conditions. How am I getting them the right data, treating their data, handling their data to get them back what they need and when they need it? Kind of plotted here and looking at one of our obviously key measures is what we call the 5 nines. What is the maximum latency at 99.99% of the time? Kind of show you a trend of kind of where we've been with storage devices as we have evolved, interfaces from spinning disks to legacy spinning disk interfaces down to NVMe optimized for solid state and the PCI with the high bandwidth and low latency. So you see the 22x improvement, continuing to work on that as being critical, and not just to focus on speed, but focus on control and focus on how we deliver on the customer requirements of consistency.
Yeah, makes a lot of sense. And so as we kind of continue to build out our architecture and fill in this, this picture of what the modernized infrastructure looks like, primary storage comes next. Of course, primary storage being a really key component. And you know, as we kind of look at what's happened over the time, a lot of the innovation here has come from the NAND that we produce. And so you think about it, in 2016, we started replacing 15K hard drives. They were all but dead. Gone were the days of more spindles to get IOP performance or short stroking hard drives within systems. That part disappeared. I think we pretty well knocked that over. This last year has been sort of this evolution of 3D and TLC really coming in and challenging the 10K hard drive world. So we've seen great disruption starting at some of the biggest data centers of the world, looking and doing the math and saying, you know what, it's not just performance that's causing this shift. What we're seeing is the value economics, the savings from doing things at scale on flash, pulling the trigger and making 10K mission critical hard drives something of the past. And as we look forward, a lot of talk and interest into what can go beyond this. And so we take our 3D NAND technology, what we think is probably the best in the world, and we apply QLC and even things like compression and other techniques to it, and we start challenging even further down into the stack of spinning media, driving it out from relevance or even dominance that it is today. Certainly true for any workload that has active data that has to be searched. And so we're very excited about what we're doing in that area.
So as you heard, I'm responsible at Micron in terms of developing SSDs, and I always say a good SSD has to start with good NAND. And what are we looking for in NAND? Well, obviously, number one, we're looking for cost. We typically look at cost in terms of density, how many bits I can get on the surface of the disk, and as I get on the wafer, as I get more and more, I'm going to get lower and lower costs. So density is one. Throughput, performance, speed. How do I get more data in and out of the device? Power efficiency, and also endurance. And I'm really excited to be up and proud to be up here on behalf of Micron and really talk about our latest NAND die here. It's our 512 gigabit TLC, 64-layer device. You can kind of see here comparing the density in gigabits per square millimeter compared to two of our key competitors, 16 and 20% higher density. That's significant. I'm an engineer, so I learned you can't say wow when you're an engineer. It's not a technical term, but that's a wow. Also in this, in ways of getting it, is not only using floating gate, but putting the CMOS underneath the array. That allows us to get this very high density. In addition to doing that, allows us to get to high degrees of parallelism to support 4 planes of operation, giving us twice the parallelism that we're getting competitors compared to using 2 planes. So this is very exciting technology for us. What we really believe is leadership and ability to go designer SSDs for cost, performance, and power efficiency. And this is TLC, and we anticipate bringing these same innovations to our QLC devices to enable even larger capacity SSDs to really go, as Eric talked about, and start to really challenge spinning media in terms of primary storage in the data center.
Yeah, absolutely. And so that kind of takes us to the next place. So you can build great media, and that's something we've done for decades now. But there's still something even beyond that, and that moves into an architectural level of the software. The software is still not at a place that it really enables Flash to do what it does. It's been designed for spinning media, and so to change that, you really have to think software in the firmware of an SSD. You also have to think software in the system stack, and you have to start with first principles and say, how do I design this differently so it's organized and optimized to take advantage of something like Flash? And that's a key part of what we're also thinking about.
Yeah, and so, I talked about NAND, and good NAND or great NAND is important to make a good drive. We also have to understand that NAND is a complex, asymmetric read and write, program times, erase times, defect management, wear leveling, garbage collection. So one of the key hidden aspects that you don't see when you open up an SSD is the firmware which is inside. How do I manage all that? How do I hide that? How do I keep driving innovations and new features in the NAND to let me go faster, do things better, reduce that latency, increase the consistency? I've got to go do a lot of work in managing it. I've got to start to expose how do I let users access different parts of my media to get different attributes. Where do I put my fast data? Where can I put the colder data? How do I break up the streams on the drive? So there's a lot of key innovations and a lot of key differentiation coming in terms of the firmware that's also inside. And I see three key focus areas there. One is the innovation in just firmware algorithms. How am I managing that to get the raw quality of service on my device? The second piece is how am I tying that together with a NAND? What are the features I want on the NAND to give me a better capability? Because I'm designing SSDs, I can go now talk to the NAND folks and influence that. How am I bringing that into the firmware? How am I bringing it into the design? So how do I bring that integrated vertical integration of those devices together? And last, we need to look at an SSD and performance not at a device level. We have to look at it at an application level. We have to not just say, how fast is my SSD? We have to say, how fast is my system to execute what it wants? We've got to go back to the people who pay us our money, which is those end users. We've got to think about how we're tying those together. How do I reach back up into the application, into the storage stack? How do I make available things like stream directives and other capabilities so that I can optimize? How do I give the level of consistency back? How do I go into the standards bodies, the participation, the openness, and the APIs to enable to build the whole system from the drive all the way up to the system so I get the optimal solution for the end user rather than talking about what my drive does compared to your drive?
Yeah, absolutely. And part of it is, and I mentioned this just briefly, but the reality is it's addressing not just that firmware, but the higher up, everything Curry just kind of mentioned. It's built for spinning media that we have to address. We have to change what traditional storage software looks like. And what's happened, of course, is for the order of, to make it compatible with a fixed slot, what we've had to do is layer on these inefficiencies. And I think you guys all know this, and we've talked about it a little bit today, but it contributes to a huge amount of write amplification within the system. What we see is companies, where actually not companies, an application writing one, byte of data turns into hundreds, even thousands of bytes of data at an SSD. And that's what we've got to wring out of the system to really take advantage of this. And it doesn't just stop there, but it really tears us away from realizing the benefits of flash. And so we've been doing a lot of work with customers and doing this in our R&D labs. And so you kind of think about what if this was optimized for flash? And there's a lot of different ways to do this, and we're going to talk to you about a few of them, but there's orders of magnitude improvement in performance if you can tear out these inefficiencies. There's latencies and improved quality of service that can be achieved taking what would be just the NAND that we have today and making orders of magnitude improvements. It's higher endurance, so taking lower endurance products and being able to turn them into higher wear and drive writes per day kind of technology. And all of this means better OpEx and savings for our customers and really moves this industry forward because we can't address the problem sitting and doing nothing in the software stack that's over and above what we're doing. And so let's explain a little bit more and have Curry kind of walk through what we found and what we're seeing.
Yeah, so I'll share a little bit of information and results we've been looking at in our R&D labs, really going back, as I talked before, about how do we tie this all the way back to the end user, not talking about what the latency of the drive is, what's the latency of the application, what are we doing to perform. So we set up a server with a 2-socket, 4 cores per socket server, 4 SSDs in it, and set up a standard KVS with RocksDB database, roughly 50-50 reads and writes. Started to look at and measure and instrument what was going on and how that application was actually talking down the drive. Now, one of the common things we talk about in SSD is write amplification. Typically, we talk at the drive level. How many writes went into the host interface to the drive versus how many go out to the NAND? And we know with wear leveling, garbage collection, other things, those numbers typically can be greater than 3 times. When we took a look at it, though, with the RocksDB database here, and how many writes the application, the database was doing to the drive versus how many were going out to the NAND, we saw it was 25. 25. For every write the application was doing, we're doing 25 writes to the NAND in the back end. When we went in and started to understand where those were coming from and optimized that storage stack, that storage layer sitting on the host between the drive and the application, we could drive that number down to 3. So an 8x improvement in the number of writes. Obviously, substantial improvement in endurance, but we can also look at what it meant to performance. And again, not performance of the drive, performance at the database. So we're plotting million database operations per second here. And you see a 8x increased performance when I change to that optimized storage stack. So the processors were idling, waiting for IOs to go back and forth and latency to complete. When I took those out in the storage stack on the host side, I got 8x improvement in the database. I've talked about quality of service and consistency. We also saw an even larger dramatic 95% reduction in both the average and in the tails of the distribution of latency, so substantial improvements in the overall control consistency in the application by changing it. And lastly, looking at data centers, one of the key limitations of data centers is power and power efficiency. So I've kind of plotted the inverse here, which is watts per million database operations per second. And you see a 7x improvement. So for the same amount of power, my database could execute 7 times more operations just by changing the storage stack and optimizing off of the standard Linux onto one optimized for flash. So substantial improvements in endurance, performance, consistency, and in power, both at the drive level and at the system level. And so this is work we're doing in our labs, working with a few partners. We're also now looking at how we have more ideas to go optimize this, bring this closer to the drive, do more things in the firmware. So we think this is a very, very fruitful area as we go forward.
You know, Curry, I'm going to save you the pain being an engineer, and I'm going to say wow for you. That's a big deal. And so we're making huge strides with this. Thanks. And so as we kind of complete off the top part of this picture, you can see there's innovations that Micron's working on with our close partners, with our customers across the board through the memories, NVDIMMs, fast storage, primary storage with our great 3D NAND, and even into the software stack. But there's a synergy element to this as well. If you don't put it together, you really don't have a recipe. Sitting alone like that, we have an architectural recipe, but we don't have the finished product. And that's where the platform comes into it and work that we've been doing. So the key piece to that is we're taking a lot of these technologies, especially NVMe over NVMe, and we're making them much quicker. And that's where NVMe over Fabric comes in. So one of the challenges that you have is without a platform or looking at any one individual platform, you capture a lot of value, but you start creating islands. And it's those islands that don't work for you. One of our customers came to us and said, look, I found speed. I know how to go fast with my solutions and your solutions, thank you, Micron. What I don't know how to do is break through that. I can only use 50% of it because every one of them stranded in an individual server. So I'm moving to a scale-out architecture. How do I break through that? And that's the connection piece that we're working on and have announced with our solid-scale architecture earlier this year. And so I thought I'd show you just a little quick video on NVMe over Fabric, and then we'll talk a little bit more. So you can see through that, our answer is this solid scale architecture we announced earlier this year. There's a couple really key important pieces to this. It's not just fast, it's not just low latency, it's not just agile infrastructure, it's all of those combined. And so our design criteria was to create a system that could scale. It could both be a scale-up system, a very traditional storage platform, or it could be a scale-out architecture. It could use open products and technologies and solutions so that it didn't lock customers in, but it enabled them to address these challenges that we talked about. It took NVMe over Fabric, but it embedded it in with the memory, the emerging memories, non-volatile memories, every part of the technology set, including the software that we've been talking about, and put it together into a package. So today, you can kind of look under the hood, and you can see that we can do 5 million IOPS per U. And that's an impressive number. That's a wow factor itself. But the reality is this is a scale-out architecture. Add another U, make that 10 million. Add another U, 15. And so as you start looking at it, what you get is incredible both capacity densities, which are important in the volume world we talked about, for the speed at which data is coming at you. We've got incredible throughput and scalability built into the system. We run this against a Microsoft SQL solution, and we can saturate 100 gig Mellanox links and deliver 11 gigabytes per second throughput. Something that is unheard of in the database world and changes the game when you're thinking machine-to-machine learning in large data sets. And it's really a solution that keeps latencies to a minimum. What our design criteria was when we started with solid scale was, how do I make latencies of a complete network solution be basically the same as a local NVMe drive? And we've accomplished that within 1%. And so incredible results, and seeing a number of different customers and partners come to work with us around this solution, and it's very exciting. And so as you kind of put all these pieces together across the top, there's other parts you influence. So we work and influence the CPU by putting our memories close to it and speeding transactions. We work very quickly. We reduce power by creating far more capabilities and operations, reducing server footprints, changing up how many nodes it takes to drive a given workload. And really through NVMe and our close partnerships, really tying together the networking and I/O part of a complete architecture that's designed, developed to change the world and take our silicon insights all the way up to the system piece of it. And so if you want to learn more, we had to go really quick. This is a half-hour presentation. We're in booth 210 upstairs, or room 210. If you want to talk to us more, you can come talk to Curry and I afterwards. We've got a mixer tonight if anybody likes to have fun. So I'm going to leave you with a short video, and thank you very much for your time.
Thank you.
There's an ancient proverb stating, if we only look at the path, we miss seeing the sky of opportunities. Well, the same goes for technology. There's a bigger, vaster, more holistic universe out there of potential, and today, all planets are aligned to maximize our data. But not just maximize it, actualize it. Transport data from simply being collected facts and figures into a more enlightened, transformative state. Deeper, useful, intentional information to guide business decisions and transform organizations. Micron is making that happen today by offering silicon to system solutions to solve problems and realize new opportunities across the globe. But what does that mean? Not just memory advancements, not just storage solutions, but a holistic business insight platform. Comprising memory, storage, software, and the system, building a data insight stack. An entire chain of throughput to push, pull, crunch, and enliven data to enlighten and embolden your business options from one application to another. We're connecting layers of technology with business intelligence, analytics, connected tech, and more for amazing results. It's the difference between following a recipe and creating your own eclectic menu. Micron helps you define what amazing looks like for your business demands, way ahead of existing intelligence trends. From silicon to system, Micron is taking data to an enlightened state and elevating it into actionable intelligence to help you, your organization, and your customers realize the sky of opportunities. You and Micron. It all stacks up.